Like,
no, not this time.
This is accurate. He needed a break.
yeah, you need a break
I didn't
from
actually have
7
a
to
break.
10.
There was like 2 days when I was actually off. Because the other school that I teach at, the spring breaks don't line up. So when they were on spring break, I was here. And then...
Wait, what was the school
So-
you teach at?
So you didn't have a spring break?
Huh?
You did not get a spring break?
I had 2 I had like a Thursday and a Friday. Like
Oh my
2 days.
God,
That was it.
That sucks.
Netflix, right?
No, he was depressed when I was 10. So how was
Oh.
your weekend?
You could grade tests and watch Netflix.
What? Anyway.
How did the class do?
So I'll give you I have your tests here. I'll give them at the end of the class because I don't want you guys distracted while I'm up here teaching.
Where did this get up?
So we're gonna jump right into it. We're gonna do the divergence theorem.
Why do you always mess with these kids?
Yo, you were
We were ready for it.
I knew it, but what are you saying? I don't put it past you to go over all the materials in quiz form.
I feel like we're
Only an only child would get like a cumulative quiz right after spring break. Like,
Are you
that's
trying to
not-
justify your answer and not being able to?
That's not something I would do. Anyway, where are we?
Professor, can you do one problem over the Stokes theorem and then move on to the divergence? Is it possible or
No.
Alright.
We'll see when we get through this. I don't expect this to take up the whole lecture time. So.
Yeah.
So we're only covering one thing, and this will actually end the vector calculus section of our
Finally.
syllabus. You guys can go around now and say, "Oh yeah, I know calculus," right? Like after today, you will know as much calculus as any civilian who's not a mathematician can possibly be expected to. Today's the day.
Oh really?
Today you grow up, you go from children to...
That didn't stop at pre-cal.
I feel like that's subjective.
It's my major. Okay, yeah.
So we're going to talk about the divergence theorem. So there was a bonus on this for, what's another name for the divergence theorem?
Gauss's theorem.
Gauss's theorem. Yeah.
Also, there's like Ostrovsky or something.
Ostrovsky, yeah. So let's call it the divergence theorem. What's the bonus? And again, this is another one of the fundamental theorems. Again, we're going to ramp up the dimensions that we're working in. And this is why on the last test I had you review triple integrals, because the divergence theorem involves a triple integral. So you will need to remember how to set up triple integrals for this one. So let's just state the theorem and jump right into it. So let E be a simple solid. Right, so a solid is a three-dimensional figure that's filled in. Simple means we can set it up using calculus. We can look at it as a type 1 or type 2 or type 3 region. Okay. So it's amenable to calculus. So E is a simple solid, and S is the at least piecewise smooth boundary. Notice that if E is three-dimensional, its boundary will be two-dimensional. So this is S here is a surface, it's not a curve. Let F be a vector field. In R3. Again, it's the normal jibber jabber. We can find partial derivatives and they're continuous, whose components have continuous partial derivatives. Then, now here's the kicker. divergence theorem tells us how to compute flux as a triple integral. It turns out that the flux over the surface S of f dot ds will be equal to the triple integral over the solid E of the divergence of f. Remember, your divergence here is a scalar. Divergence is a scalar, so this is just a triple integral of some function. Okay? One comment I want to make at this point, which it just occurred to me to make it. A side note. Which incidentally might help you with the next homework. Suppose suppose the divergence of f is a constant, right? This idea sort of applies in general, but it's easier to see when it's a constant. It's more straightforward. Then what you can say is the flux is going to be equal to, if it's a constant, I can factor it out. Now remembering your calculus 3, the triple integral of 1 ends up being what?
The volume.
It's the volume of the. So this is divergence of f times, this is a regular multiplication, times the volume of E. And in other words, so usually when we apply this idea, it's in the infinitesimal case. Sure, on the grand scheme of things, things can be variables, but if you zoom in on a little part, approximate with a tangent plane, in that little region you can sort of think of things as constants if you zoom in far enough. And so this basically gives you the idea that the flux over the volume of E is approximately equal to the divergence. And usually we apply this on the case, i.e. at the point x0, y0, z0, the divergence of f evaluated at x0, y0, z0 will be approximately equal to the flux through a small region of x0, y0, z0 divided by the volume of the region. So in other words, the divergence, we sort of discussed this before, what it sort of means. And it was a kind of a measure of spreading out. If you think about what that means, it's kind of you describing what is passing through a region by describing what's coming in versus what's going out. So, right, so the divergence is a measure of how much thing is spreading out from a certain region, but the flux, what the flux is, it's the amount of stuff that's passing through a region. So it turns out that the divergence is sort of a measurement of flux on an infinitesimal region. So if you dissect your surface into a bunch of little rectangles that are getting smaller and smaller and smaller, the divergence at any point is kind of telling you the unit flux at that point. Right? So flux in general is the amount of stuff that passes through a region, and the divergence is a function that sort of tells you, if I zoom in on one region and look at that small region, how much stuff is passing through that, that's what your divergence is. Right? So it's a measure of how things are spreading out, which is a description of basically how much things are coming in versus how much is going out, how much stuff is passing through. So this is a useful idea, and I think there was a homework problem where that idea would be useful. But that was just a side note. Let's move on. Let's do some examples. So again, it's the same deal like with Green's theorem and Stokes' theorem. You need to know what the theorem says, the equation that it involves, and be able to compute both sides of this equation if I give you a situation. So let's see an example here. Let's do the first example. Let f be this vector field. 2x minus y.
Sorry.
Minus y plus z. Z. S is the boundary. It's in the first octave. So we know that flux is equal to this guy. So by divergence theorem, I can actually compute that guy by computing this guy. Right, so we actually know how to compute this directly, but we're not going to do that because notice here, what kind of region is this?
It's like a triangle.
It's a tetrahedron, right? So this is a plane where if you plug in y and z equals 0, you get x equals 6. Plug in this 2, you get y equals 3. Plug in x and y equals 0, you get z equals 6. So it's this plane here. The coordinate planes means the xy plane, the yz plane, the xz plane. And so we have this tetrahedral region here. Sort of like a skewed pyramid. Okay. And so S is the boundary of this region. So notice that S has 1, 2, 3, 4 surfaces. There's the xz plane, the yz plane, the xy plane, and then this plane that's coming over here. So there are 4 regions. So if you were doing this directly, you would need to do 4 double integrals where you're setting up a flux vector over each of them, right? But here, it turns out we can do all of that with one triple integral. What's the first thing you want to do here?
Find the divergence.
Let's find the divergence. Let's find the function that we're going to integrate. Divergence of this?
2. -2.
Plus
And 1.
So remember the divergence is the partial of the first component with respect to x plus the partial of the second component with respect to y plus the partial of the third component with respect to z, in case you remember. So this is your P, Q, R, all right, and this gives you the divergence. So your divergence here ends up being 1. And so 2. Let me get rid of this.
Wait.
F is this. We're in the first octant bounded by the plane x plus 2y plus z equals 6. So now we know that the flux is equal to the triple integral of 1 dV. Right? I mean, which if you know how to find the volume of a random tetrahedron, sure you can apply it here. But I don't, so how would we set up this triple integral?
It's just dx, dy, dz.
Dx, dy, well, it depends, you tell me.
Fine.
This one can actually be set up in any one of the 3 orders. So what's the first thing you want to do here? Easy.
Figure out what order you want to integrate in.
Okay, so how would you do that?
Okay, we could do z. Let's do z.
Sure, I know rectangular, but who are you solving for?
Z.
So you can solve for z. Which means I'm thinking of my region of projection as this guy, right? So that would be in the xy plane, this guy, where that's 6 and that's 3. I actually know the equation of that. It would be if my z I plugged in 0. So it's probably easier here to solve for the x. That means x is equal to 6 minus 2y. Just to avoid like fractions. And so how would I set that up now?
So first integral from 0 to 6 minus x minus 2y.
Which one are we talking about? This one?
Yeah.
0, so that's my z surface. That's the bottom one going up to the top one is this. 6 minus x minus 2y.
Then your y. So that's from dz. Then your dy is from 0 to 6 minus 2y.
X. X goes from
Oh, right.
0 to 6 minus 2y. And then finally your y would go from 0 to 3. Sure. And you put that in the oven, and I think you get 18. It comes out as this delicious dish.
How could it be 18? If you made a cube out of that, it would be 6 times 3. Oh, times 3, okay. Sorry.
Yeah, I mean, it's going to take some work here. You're going to plug this in, and then you're going to integrate that with respect to x. Then you're going to get another function, integrate that with respect to y, and then you're going to plug in the limits. I think eventually you get 18.
So it's a third of a cube. That means it's a third of a cube. 6 of a 6 by 3 by 3 cube.
Would it?
It wouldn't be a cube, no.
Like if
He's
you
saying
made
it's a third of a
If you
cube.
made a cube out of that and then cut it into thirds, isn't that what that tetrahedron? Man, never mind.
No, because shouldn't that be 6 then?
No,
I'm not sure. He's saying you have a 6 by 6 by 6 cube, and he cuts off. He's saying that you cut off 2/3 of it.
But
I would just do that. I mean, it's not going to be that long.
shouldn't they all be 6?
I mean, at this point, I'm not teaching you guys how to integrate. I'm just teaching you guys how to set something up. Let's do another example. And this one is asking you to do both sides. The E be the solid region. Verify the divergence theorem for
He's not that, he's enthusiastic.
He's passionate.
Take my passion elsewhere.
Just comes out of what you said.
Oh. Isn't the divergence of then 0? Yes. So I know on the test for side I do first. Yeah. So I know exactly what I should be getting. Okay. So, of course, when it says verify, it means you do have to do both sides. Verify means compute. This is a parenthetical statement. Compute both sides of. And ultimately, you need to show they're equal. Right? They should be equal. That's what the divergence theorem says. And if they're not equal, you made a mistake in one. And it's clear which one you would have made a mistake in this case. So let's do the right side first. That one's clearly the easiest. Notice here that the divergence of f is equal to 0. So this means the flux is equal to the triple integral over e of 0 dv. You have a definite integral of 0, the answer is 0. So the flux is 0 here. So this is a vector field in which it's kind of like in any region you look, the amount of stuff coming in is exactly the same as the amount of stuff coming out, so it's almost like everything is stationary. There's no divergence. So you can't really see something as passing through. It's like everything looks stationary. 2, let's do the left side. Probably going to be a little bit more work. So how do we do the left side here? First, let's draw a picture to see what we're dealing with. So what does this look like? What's this guy? Paraboloid.
Isn't it going
Oh,
down?
it's a negative paraboloid. So it starts at 4 and comes down and the xy plane forms the other boundary. So we have this object here. So how would I go about setting up the flux integral?
Find a normal vector.
Parameter.
So I need to find a normal vector to this surface and this surface. Oh, and again, the divergence theorem, I don't think I wrote this down, but it's set up for positive orientation. So unless otherwise stated, I'm most assuming that my normal vector is point. So be sure to scribble that in. Okay. But the important thing you should realize here is you want to think of this, dissect this into two surfaces. There's an S1 and an S2. Okay. So let's deal with S1. So how would I find the normal vector for S1?
Just use
Minus part with respect to x, minus part with respect to y, is 1. Where my f is this guy. So it's 2x comma 2y comma 1. That's my normal vector. And so then what?
find the double integral.
Right, so the flux is going to be equal to the double integral over S1 of f, which was what? 2z comma x comma y squared, dot product with 2x comma 2y comma 1. A. D is in ready in this region here. Okay, and how do I deal with that?
Will you get rid of the first term because z is equal to 0 on the xy plane?
Come again?
Like if you're changing to polar coordinates, so you're doing r d theta.
Sure, but my z is not equal to 0 here. My z is, I'm doing S1, which is this surface.
But if you're aren't you looking at like on the xy plane the projection of it?
That's S2 though.
That's for S2. For S2, z is 0. Here, our z is a function.
Plug in Z.
So I replace it. My z would be, it was 4 minus x squared minus y squared.
Okay.
Let's see if this becomes something nice. So it's 16x minus 4x2. I don't see anything simplifying here, do you guys? What about this part here?
Well, you take a 4x.
That's 4 minus 4x times x squared plus y squared, right? Okay, so let's plug in our limits. 0 to 2 pi, r goes from 0 to 2. And this is 16 r cosine theta minus 4r cubed cosine theta minus, well, plus 2r squared cosine theta sine theta plus r squared sine squared theta, all of that times r dr d theta. And you see that, and at first you start cursing Javon out in your mind, saying, look at this integral that this dude gave us on this test. We'll have like 5 minutes left. But then you realize, oh, it's on 0 to 2 pi. So pretty much anything with a sine or a cosine do not apply. So I can ignore those guys because it's a definite integral on the period of cosine and sine. So those guys, ultimately, once I start plugging in, integrating them and plugging them in, they're all going to give me 0. So the whole thing just sort of collapses into this guy. R cubed.
Wait, wouldn't you get rid of theta? What?
Hmm?
Never mind.
Because when I integrate with respect to r and plug in the constants, this is just going to be a constant. The integral of cosine is going to be sine of theta, plug in 0 to 2 pi, that's going to go to 0. Same thing is going to happen here. This guy I can think of as sine 2 theta, right? And so when I integrate that, I get cosine of 2 theta over 2. Plug in 2 pi and 0 into that, that's also going to die. So all of these three components here, they're all going to go to 0. I'm only left with this guy times r dr d theta, which gives me this guy. So the sine squared, I can think of that as 1/2 times 1 plus cosine, 1 minus cosine 2 theta, times the integral of this is going to be r to the 4th over 4, is 2. So if I plug in 2 here, 2 to the 4th is 16 divided by 4, so that just gives me 4 times 1/2, so that just gives me 2. This part is going to go to 0, so it's ignored, so this is just 2 times 2 pi. We do S2. That one's easier because the surface is 0, and so you know that your n is going to be 0, 0, negative 1. And so the double integral over S2 is going to be a double integral over d of 2z x y squared times so that just ends up being the negative of y squared dA.
Ron, did you forget a cosine cube?
Where?
The negative 4x cubed? It goes to 0.
Which part? Which part?
We had
Over here?
negative 4x cubed, and then yes, there was. Did we write down a cos cube? Because cos cube wouldn't automatically go to 0, would it?
There was no cos
The-
cube.
Yeah.
Was
I
there?
think he simplified it too.
There was no cos. There was no cosine cube.
Well, why not? Because we had.
He
we had
simplified
I words too.
it. That's when
Yeah.
you took the 4x out.
Uh-huh.
I factored out something so that there was an x squared plus y squared,
Oh, okay, okay.
and then that came in. But it would also work with cosine cubed, right? Because if you had cosine cubed, you would think of that as what? Cosine squared times cosine.
theta. And then you could change it as 1 minus.
Does that all automatically go to 0? Because that you just integrate 1 minus sine squared.
Doesn't that sound the same period? So wouldn't
It would have the same.
it would still go to 0.
It would still go to 0 ultimately, but I ended up not having to deal with that because of how I simplified. Anyway, at this point we end up with this guy. My y squared is going to be r squared sine squared theta times r dr d theta. Double integral from 0 to 2 pi 0 to 2 minus. You'd realize that was exactly the same integral. That's exactly this integral. So we already know that answer. It's minus 4 pi because of the negative sign here. So this means the double integral of f dot ds is equal to 4 pi minus 4 pi. Pretty much one more example you have to do. So this asks me to compute the flux integral. It didn't ask me to verify anything, so there's no real need to do both sides of the equation. Seeing as this guy is probably not someone I'd want to deal with directly, it doesn't look very nice. I don't want to have to dot product with something. I'd use the triple integral version. So there are times when doing it directly it's easier, but it's definitely more rare. That's definitely the rarer case, especially in a calculus class. But yeah, by the divergence theorem, the guy that we care about, the flux integral, measure of how much stuff is passing through this region under this vector field, is just a triple integral over the region of its divergence. So it's going to be the triple integral over E. So the divergence of this would be the partial with respect to x of the first component to x plus the partial with respect to y of the second component plus the partial with respect to z of the third component, which is just 0. So computing that triple integral is exactly the same as computing the flux. So how would you set this guy up? Quickly draw a picture to just see the relative positions of things. What kind of guy is this?
Cylinder.
It's a circular cylinder running along the z-axis. And this guy is a plane, right? So in the xz plane, it passes through z equals 6 and x equals 6. So it's slanting this way. So it's just going to look like this. And the xy plane, which is the bottom part. So if I were doing this directly, I would need to do 3 double integrals, one for the slanted surface, one for the cylinder, which I'd parameterize and have to do the cross product for the normal, and then for the bottom surface, where it's just like 0, 0, minus 1. But I can get around all that by just doing this one triple integral. So I'm going to choose my region of projection to be in the xy plane, so the 2 outer integrals are setting up that region, which is just the circle of radius 2. 0 to 2 pi, 0 to 2. My z is going from the xy plane, which is z equals 0, up to this surface, which I know is going to be z equals 6 minus x. But my x, because I'm switching to cylindrical, is r cosine theta. And my x is r cosine theta, and the r dz. So this here is just x, and this here is just x, because my z is 6 minus x. And now I'm going to just compute this guy. Or do I have to? Does anyone beside Kakab want to see? Okay. He's busy copying. Okay, so this becomes r squared cosine theta. Now the integral of this is just going to put a z here, so I'm going to plug in fundamental theorem, plug in this, minus plug in 0. By doing that, then Benita would get her way, and I will not have that happen. She's never here with me. So, 0 to 2 pi, 0 to 2 of 6 r squared cosine theta, which again, that would go by 0, go to 0 by previous reason because there's a cosine here, minus r cubed.
Yeah, I'm missing it.
What, 3 from in front?
Yeah.
Minus r cubed
Isn't it?
Yeah, minus r cubed times cosine squared theta. So this becomes minus r to the fourth over 4 between 0 and 2. And again, you plug in 2 here, that's 16 divided by 4, which is 4. It's a minus 4. I pull that out, that's minus 12 times 0 to 2 pi of cosine squared, half angle formula, 1 plus cosine 2 theta d theta. My cosine 2 theta is going to go to 0. And so that just becomes minus 6 times 0 to 2 pi d theta, which is minus 6 times 2 pi. So again, the interpretation of negative flux sort of means that there's more stuff coming in than is going out. That's the interpretation you get. So on average, if you zoom in on some region in this thing, there are like very large vectors going into that region and relatively small vectors exiting that region. So that will give you a negative divergence. So let's just do a summary here of what we've done throughout all our calculus classes. Just like Iron Man says in the Infinity War theory trailer, everything we've done has led up to this. So it started out pretty innocently back in Calc 1, where we learned something called the fundamental theorem of calculus, which basically says the definite integral of the derivative of a function is actually equal to the original function evaluated on the endpoints. Now, that guy was working on a straight line that lived on the xy plane, on the x-axis. Okay. And that was good enough for all the things we wanted to do. That allowed us to find the volume under curves. It allowed us to add up a lot of things very efficiently, an infinite number of things very efficiently. And there's a whole host of things that came out of learning that. So that was the fundamental theorem of calculus, one part of it anyway. And then we generalized this integral, and again, we went on to double integrals and triple integrals, but they were always sort of confined to the axes or the coordinate planes. And so when we finally come to this class, we started to generalize a little bit. And we got the fundamental theorem of calculus for line integrals. And so that one says, what does that one say? Fundamental theorem of calculus for line integrals.
Integral of the gradient of f is equal.
The integral of the gradient of f
dot dr
is equal to f at
rt
final point minus f of the initial point. And this guy was sort of, now we could do essentially the fundamental theorem of calculus over some arbitrary curve. We were no longer confined to the axes, but we can do it over some general curve. And one way you can think about this is that the gradient of f was kind of like a derivative. It was kind of like some sort of prime that we were taking that was meaningful in the context in which we were working. And it turns out, if we take the integral of the derivative, it was really the original function evaluated at the endpoints, right? But it was more generalized than the fundamental theorem of calculus, because now we could escape the axes. Then we move on to something a little bit higher. We moved on to Green's theorem, which for the sake of comparison, I'm going to state it in the opposite way in which we usually state it. So I'm going to put the double integral on this side. And what were we doing here? What's the double integral part of Green's theorem?
Qx minus d1.
Partial q with respect to x minus partial q with respect to y dA. And that was equal to
Work. Isn't that also like work? Could you have said that too?
this was work. Okay. But I'm sort of comparing these theorems to each other. And so this guy operated in R2 for a general region. So we really started upping the dimensions here. We're not only on a one-dimensional curve where our endpoints were zero-dimensional entities where they literally just numbers we could plug in. Now we upgraded to the part where our boundary is a curve on its own, which we can call C. And instead of an interval, we have a two-dimensional surface. Right? We upped the dimensions a little bit. So before we were integrating along a one-dimensional space where the boundaries were zero-dimensional. Now we're integrating around a two-dimensional space where the boundary is one-dimensional. We just up each dimension by one. You'll notice here that if you think of a single integral as the original function, then a double integral is going to be the integral of that function. And this guy, again, is sort of like a derivative. It's a derivative that meant something in the context we were working in. So again, we have the integral of the derivative of a function is just the original function evaluated at the boundaries, which in this case is a one-dimensional curve. But even that wasn't good enough. We wanted to go even further. Right? Because here this region was bounded in the xy plane. We were stuck in the coordinate plane. We wanted to do sort of like what we did with this, we wanted to do with that. Let's take it out of a flat plane and move it into a three space where it can take on a life of its own. And that ended up being Stokes' theorem. Now in Stokes' theorem, again we up the dimension. We have a two-dimensional surface, yes, but now we're in a three-dimensional space. The region and the boundary is still two dimensions and one dimension respectively, but now we have some more freedom in how it can move, similarly to how we got more freedom by jumping from this to that. Right? And that was what gave us Stokes' theorem. And Stokes' theorem says and again, this I can think of as some sort of derivative. So the integral of a derivative of a function is sort of the original function evaluated on the boundary. Taking it up even higher, we get to the divergence theorem, where now we have some sort of object. Now this is three-dimensional. We can get a projected region if we want, but the important thing here is that now S is the boundary. The boundary is two-dimensional, while the region E is three-dimensional. And that gave us the divergence theorem. Whereas if I think of the original function as a double integral, the integral of that would be a triple integral, and I integrate over a derivative of the function. And I get the divergence theorem. So these are all sort of saying there's a common thread that goes through calculus that basically says the integral of a derivative is the same as evaluating the original function on the boundary. And we can extend this idea to be in higher and higher dimensions. And as I was saying, this is sort of the level of calculus that any civilian who's not a math major would expect it to get up to. So we never really go beyond 3 dimensions here. If you want to go beyond 3 dimensions, you can become a math major and study that, study more real analysis and generalize an integral even more. But that's basically it. This was kind of the summary. This is what calculus was leading up to, the fundamental theorems. And calculus being the mathematics of the physical world and sciences, right? This is the math that we best know how to describe physical reality, is calculus. It ends up being in terms of these guys, and I sort of talked about what these guys meant, about how curl is just sort of a measure of rotation, about torque, rotational forces. This one is talking about how things are spreading out, right? This one we know we can find volume and area, and we can use that in terms of the rate of change. Idea, we can find acceleration and blah, 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 and all that stuff. So this is kind of the summary of calculus, and we finally got to the end. So I feel like we should throw a party or something. Yeah, let's get out of here. I'm kidding. Well, technically that's all I wanted to cover today, because we are now going to, it's sort of a bittersweet moment. We're not even going to stop to really ponder what we've come up with. But yeah, calculus, the idea of the fundamental theorems. This is the connection that is bounding physical reality, and we can use these integrals to apply to a whole bunch of stuff, because our vector fields can really take on a bunch of interpretations, and so these integrals can describe a bunch of physical phenomena in any dimensions up to 3 dimensions. And we'll stop there. We'll start linear algebra in the next class. And oh, I have your test to give back, and then you can get out of here.
Do you do worse or better?